Okay, hello class. This is Mr. Mellinger, AP Chemistry. This is your lesson for day 5, August 30th, 2019. And it's going to be a lesson on ions, isotope, and atomic radius. So in the previous lesson, we learned about the structure of a basic atom and how to construct a basic atom from the periodic table. Now we're going to introduce you to 3 terms, and these terms are used constantly in chemistry. You'll probably hear at least one or more of them every single day in this class. So become comfortable at what they mean. So how much space is there in an atom? If you put the nucleus of a helium atom floating above the middle of a football stadium, right there, then the electrons, its 2 electrons would be buzzing around in the upper deck. And actually they'd probably be even farther away than that. So you can see there's a lot of space between the nucleus and the electrons. So the most of the volume of an atom is made up of empty space. Okay, so what is an isotope? A key term, and learn this immediately what this means. An isotope is an atom of the same element, but with a different number of neutrons. Okay, so if you look at this, this represents a lithium atom. Now, how would you have known that if it didn't say so? Well, it has 3 protons. Lithium must have 3 protons or it's not lithium. So this is a lithium atom. It has 3 protons, it has 3 electrons. Each of these 2 lithium atoms, the one thing that they have different is the number of neutrons. So these are 2 isotopes of lithium. So we learned that a typical lithium has 4 neutrons, but occasionally we come across a lithium atom with only 3 neutrons. And those are referred to as isotopes. Their electrical charge is the same, as they have the same number of positives and negatives, and they're both electrically neutral, but they have different masses. And the different mass can have some different chemical properties. Okay, so the notation for an isotope is it's drawn in kind of the reverse fashion of what the periodic table is. In the periodic table, usually the atomic number comes above on the top of the box, but in this case, you put the atomic number down on the lower left side of the element symbol, the atomic symbol, and then the atomic mass or mass number goes up on the top. Now notice there's no decimal in the mass number, and that's because a specific atom of lithium, in this case, either has a mass of 6 or a mass of 7. It doesn't have a decimal mass. It's not somewhere in between. That's done on the periodic table to show the average mass of all the different isotopes of lithium atoms. And we'll learn how to do that calculation at another time. So notice that the atomic mass is on the top, the atomic number is on the bottom. This is the opposite of the way it's done on most periodic tables. Okay, what is an ion? So we know atoms have 3 different parts to them: proton, neutron, electron. An ion is an atom of the same element that has a different number of electrons. So if you look at the atom on the left here, it's an electrically neutral lithium atom. It has 3 protons and 3 electrons. On the right, what you see is a lithium atom with 3 protons but only 2 electrons. That's referred to as an ion. So the pure element atom is the one on the left. The ionized lithium atom is the one on the right. It's lost an electron. That's going to be a very important factor. You're going to deal with this concept almost literally every day, is this idea of ions, atoms that have gained or lost an electron. What is a cation? So a cation is an atom that has more protons than electrons. In the case of lithium, if it lost an electron, it has 3 protons but only 2 electrons. So it has a net positive charge. It has more positive than it has negative. This lithium ion is an example of a cation. It has a positive charge. Okay, so the little mnemonic for that is this dude, the Cheshire Cat, is a positive cation. So cations are positive. So the happy cat is a positive cation. An anion is an atom that has more electrons than protons. It's taken an electron away from some other atom or gained it in some other way, and so it has more electrons. So if you count the number of electrons here, you'll count 10. And if you count the number of protons in the nucleus, there's only 9. So this has what it's referred to as a net negative charge because it has one more negative electron than positive proton. In both cases in the case of anions, we're not concerned about neutrons. Okay, they're of no concern of this. Okay, so this fluorine atom is an example of an anion. It has one more electron than proton. An anion has a negative charge. So this grumpy guy is a negative ant. He's mad. He's negative. He's a negative ant ion. It's really anion, but you can go along with this negative anion. Okay. All right. What is ionization energy? And over in the yellow box, that should be ionization energy. So ionization energy is the amount of energy that is required to pull an electron away from its atom. So this man represents ionization energy. The ionization energy must have greater pull on the electron than the protons do. Normally the protons are pulling on the electron. That's what's keeping it from flying away from the atom. But if somehow you can put energy into that electron to liberate it from its atom, then it will get pulled away. Notice there's more than one electron. So that first electron, the outermost electron, which we call the valence electron, that has the lowest ionization energy. It's easiest to pull that away. If that gets pulled away and you then want to pull away one of the remaining 2 electrons, it will take more energy. They're held more tightly because they're closer to the nucleus. If you pulled one of them away, it would be a higher ionization energy. And then if you wanted to finally pull the third electron away, it would require even higher ionization energy. So the energy the man with the rope must use to pull the electron away from the atom is the ionization energy. Okay, so how do ionization energies change across the periodic table? Ionization energies increase as you go up a group, that's from bottom to top of the periodic table, and as you go to the right, from left to right on the periodic table. So the elements in the upper right-hand corner, and we can just name a few of them: oxygen, fluorine, helium, neon, O, F, H, E, N, E. Those have very high ionization energies. It's very hard to pull the electrons away from them. The elements down at the lower left of the periodic table, cesium, barium, francium, strontium, rubidium, they have very low ionization energies. Those are the easiest elements to pull an electron away from. It doesn't take nearly as much energy to pull an electron away from them. So the lowest are on the lower left, the highest are on the upper right. All right, so where are the highest ionization energies? And we just mentioned that. So this kind of gives you a perspective of that. Doesn't show every element, but you see that the higher elevations are on the upper right, and the lower ones are on the lower left. So ionization energy is greatest in the upper right-hand corner of the periodic table where helium is. Okay, what is electronegativity? So this little man represents electronegativity. Electronegativity wants to pull in an electron. Now, there is another concept called electron affinity. For the time being, for just the next, let's say for the next few days, we're going to treat them as though they're the same. They're basically how much they want to pull in an electron that is not actually their electron. Okay, so this atom If this atom wants to very strongly pull in an electron from the outside, it's said to have high electronegativity or electron affinity. So electronegativity is how much an atom wants to pull an electron toward it. Okay, so how does electronegativity increase? Electronegativity increases as you go up a group and right in the periodic table. So it's exactly the same as ionization energy. So with one exception, though, one very important exception that we'll get to. So the elements in the upper right, such as oxygen, fluorine, chlorine, sulfur, have high electronegativities. Now look at the elements on the far right, and we're going to learn the names of these different areas of the periodic table very soon. But helium, neon, argon, krypton, those ones on the far right column, they have no electronegativities, and we'll talk about why that is at a later time. But other than that column, that right-hand column called the noble gases, oxygen, fluorine, chlorine, and sulfur have high electronegativities. And if you go down to the lower left again, strontium, rubidium, cesium, barium, and so forth, francium, radium, they have low electronegativities or electron affinities. And there you see again a perspective table showing the high on the upper right, the low on the lower left. And again, you'll notice that on the right-hand side of this, you have fluorine, chlorine, bromine, but you don't have the noble gases, helium, neon, argon, and so forth. So they don't have electronegativities at all. Electronegativity, by the way, is measured in a numeric scale from 0 to 4. So fluorine is the highest with 4, and everything else has a number relative to that that goes down until you see cesium in the lower left has 0.7 electronegativity. The electronegativity is greatest in the upper right-hand corner of the periodic table, not where helium is, actually, but in the upper right-hand corner. Okay, so what happens when you put an element that has a low ionization energy, meaning that it easily gives up, it doesn't take much energy to pull its electrons away from it, and you put it next to one that has a high electronegativity, which means that it wants to pull in electrons from somewhere else. So lithium has a low ionization energy, so it easily loses electrons. It doesn't take much energy to take out that, to remove that valence electron that you see in lithium. Fluorine has high electronegativity, so it easily gains electrons. It really wants to pull electrons in. So the answer is that lithium loses an electron to fluorine. Okay, so that electron moved over from lithium to fluorine. Okay? And this is a common occurrence in chemistry, and we'll talk about this in the near future. Okay, atomic radius. The atomic radius, our definition of atomic radius will be the distance from the center of the nucleus to the outermost electron. So the atomic radius is the distance between the center of the nuclei and the outermost electron. Atomic radius is the size of the atom. I'll give you a more technical definition later on, but this is effectively what it is. That's not an exact distance because those outer electrons buzz around. They don't actually stay right on a perfect circle like that. So it's not exactly like the radius of a circle, but it's close enough for our purposes at this time. Okay, so how does atomic radius change across the periodic table? Atomic radius decreases as you go up the periodic table and right in the periodic table. So as you go from bottom of periodic table to top, you have fewer and fewer orbitals. Remember, each row in the periodic table as you go down increases the number of orbitals, and therefore the atom gets bigger and bigger and bigger. What seems a little counterintuitive, doesn't seem to quite make sense, is why the atomic radius decreases as you go from left to right. Take the second row, for example. You go from lithium to beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. the atomic radius gets smaller. The atomic radius of neon is much smaller than lithium. Why would that be? If you keep adding protons and electrons as you go from left to right, each one of those elements adds another proton and another electron. If you keep adding parts to an atom, why would its atomic radius get smaller? So as we move to the upper right-hand side of the periodic table, ionization energy and electronegativity increase while atomic radius decreases. So memorize these patterns right here. But why does that happen? Why does atomic radius decrease even though you're adding a proton and an electron each time you go to the next element to the right? And here's a plot of atomic radius. So what is happening is this. As you add protons and electrons, you're putting more positive protons in the middle of the atom, into the nucleus. They therefore exert more pull on the electrons on the outside. And so the electrons, each time you add a proton to an element, even though you're adding an electron, though the electrons in the valence orbital, the outer orbital, start to get pulled in because they have more of a positive charge in the nucleus that's attracting them. And therefore, they get smaller and smaller. So what this chart is telling you is, let's go to the yellow dot on the upper left-hand side there. That represents lithium. That's the second row of the periodic table. And you'll see as you go to the next element, the next yellow dot down, that's beryllium. The next one down is boron, carbon. You can see as you go from left to right along the second row, those yellow dots represent the second row, then the atomic radius actually gets smaller. Okay? And PM, by the way, the measurement PM is picometers, and that's 1/1 trillionth of a meter. Then as you go all the way down to the bottom of the yellow, it jumps back up and you see that top red dot there. That's the first element in the third row, and that's sodium, Na. As you go to the next one, magnesium, it gets a little smaller, and then aluminum, smaller, silicon, smaller, phosphorus, and so on. As you go across the third row, they get smaller and smaller. Again, the reason is because you keep adding protons to the nucleus, and they pull in the electrons in tighter and tighter and tighter. And that happens in all of the rows. So here is that explanation. As you grow across a period row, more protons are added to the nucleus. The electrons are pulled in with greater force. This means the atomic radius becomes smaller. The energy required to pull an electron out, ionization energy, becomes greater, and the ability to pull an electron in, electronegativity, also becomes greater. So increasing the number of protons does those three things. Smaller atomic radius, harder to pull the electrons away because of that strong positive charge in the center. And the strong positive charge in the center also wants to pull in electrons from the outside. So that's high electronegativity. As we go down the periodic table, more orbitals are added. This makes the atomic radius larger. This one's kind of obvious. As you keep adding a second and a third and a fourth orbital that are farther and farther away from the nucleus, the atomic radius gets bigger. And the outer electrons are farther from the nucleus. This increased distance makes both the ionization energy and the electronegativity less. And that takes care of our lesson on isotopes, ions, and atomic radius. We'll see you in class.